Okay, so to sort of continue and get back to kind of the motivation for this, which I should have shown earlier, if you kind of take, this is histological changes in a trabecular bone sample from patients, and this is then slices that you can take from sort of these samples, and you end up with images that look kind of like this. And so kind of the goal we have with this is to be able to say what actually changes between an image like this and an image like this. And our eyes can see lots of things, and we can make statements like this seems like it has sort of denser packed or better linked, and these are sort of further apart, and there's more white spaces there. But what we really want to be able to do with information like this is quantify it, particularly if we're trying to compare this sample and this sample. Coming up with exact words that express that well are difficult. And, what's the change that we see here? Are they sort of closer together? Are they more evenly distributed? What are those kind of differences that we see? And in samples like this, you don't know, this isn't exactly the same region as before. It's not the same kind of sample. It's not the same kind of cells exactly. And so how do you measure those changes and try to understand what happened between step A and step B? And that's sort of what we're going after with this. So we were at sort of the shear distributions where we saw sort of the points shift from here to here to here, and the nearest neighbors change here so that we only have this distribution with the orientation in negative 90 and 90, so the x-axis, and we don't have any of the connections between the top and the bottom anymore. Now we go to stretches, and so this stretch tool is this kind of weird formula I showed before, and basically what it does is it makes things either cluster towards the middle if it's a positive number, or if it's above 1, it clusters towards the middle, and if it's less than 1, it clusters towards the edges. And so it basically keeps the moves the objects in kind of a nonlinear way so that they're more densely packed in certain regions than others. And so what would you expect to happen to the nearest neighbor distance in this sample? Yeah.
If you're at the edge, the distance will decrease. If you're in the center, it will increase.
Yeah. So what would that do to the overall distribution?
Depending on the function, how well distributed the function is, then it might average out to 0. Maybe, I don't know.
It doesn't.
Total distance, total change.
Right. So before the distance was here, let's say, 1 or, point. So here, all of the distances are the same, and the orientation is kind of random. And what would we expect the distance to be after?
The average distance. The average distance between.
Or the distribution in distances.
The distribution. Oh, okay. So then. Well, you have a wider distribution because standard deviation of the value of distance will increase greatly.
Yeah.
The average might stay the same depending on how the function is made.
Yeah. I mean, the average is difficult to assess just by looking at this image, but the standard deviation will certainly get higher. And so, and with the angle, do you expect any differences? So we can then look. So we see that the distances, when we have 1, and of course, all of the distances are grouped at 1. The average distance is quite clear. When we have a factor of 0.5, we see that there's now sort of a wider distribution. When we have a factor of 3, then we see that there's an even wider distribution. So this shows the number of cells that have that and the distance that each one corresponds to. And so we see that those distance changes, and we probably can't tell exactly what it will be, and depending on the system, this average distance can change more or less. But ultimately what we see is that this distribution goes from being a single peak to being a much broader peak. And the further this value is from 1, the more broad this peak will be, because the more sort of variability you have in your system. We see with the angles that there's not really much of a change in the distribution of angles because the samples aren't changed differently in x and y. They're just changed differently based on where they're positioned. And so we wouldn't have really expected the orientation to change substantially. So now we have the last one, which is sort of this weird swirl. And this is sort of what swirl looks like at 0. Nothing. It's exactly the same as the system you put in. If you have a swirl of 4, you sort of start to get this pattern where each layer is sort of twisted slightly more than the layer outside of it. And then you have a pattern of 8, if it's 18 and then it's swirled so strongly you kind of can't tell what the original structure was anymore. What we have here is that we again see that the nearest neighbor distance changes. So at a swirl of 0, everything's packed at 1. And as we swirl it more and more, this distribution gets shifted closer and closer to 0. So we get a broader distribution, but the values are decreased as well. And so there's a few objects that remain sort of a distance of 1. The rest of the objects get much closer to their nearest neighbor distance. And so what's important to know with something like nearest neighbor distance is that it's not conserved. You can have all of your points right next to each other, and your nearest neighbor distance will be basically 0. Or you could have all of your points sort of as far apart as possible, and your distance will be 1 or so. But there's no rule that says like the average has to be the same before and after. This can change completely. And then with the orientations, we see that we get some sort of weird structures that come out of this orientation, so that when we had it at 0, and this graph's a little bit hard to see, we sort of have these 4 peaks here, this pink line. When we have it at 4, we see that these peaks shift a little bit to the right and get a little bit broader. And when we have it at 18, they shift to the right even more, and they get even broader. And so if we go back to this image, we see that we sort of start to get kind of these structured things because this line of points is closer to itself than it is to any of these other points, and so the angle isn't completely random anymore. But there's more diversity because you don't simply have this sort of along your Cartesian coordinates, you have more possibilities of what the angles can be because the objects are sort of shifted. And so kind of what we notice with this system is that orientation seems like it could be useful, but it's pretty much random in most of the samples we've seen so far. It's a problem because if one side is 0.01% closer, then that actually doesn't make that much of a difference. You wouldn't expect your entire structure to change by something being 0.1% closer. And so if you show this with like shearing, for example, we did it with 0.5, but if you do shearing with 0.01, as soon as you shifted these points just a little bit, it's no longer closest to the ones in the top and the bottom, so you have a complete drastic shift in your orientations. And so that means it's not a very stable metric on a system like this, and that's not something that we want to have. We want to have small changes in inputs, have small changes in outputs typically. We only extract kind of one piece of information, and it's kind of difficult to create metrics. And so we saw that for compression, this was fairly easy, that when the nearest neighbor distance decreases, but everything else stays the same, that's a pretty good sign that the sample's been compressed. But sort of what happened with swirling and what happened with stretching were similar. It would be pretty difficult for us to quantify that this system was swirled and this system was stretched with the metrics that we have. And then you have sort of things like angle variability that we saw with this sample. That you have this getting broader, but that's not really your angle getting more variable. That's sort of these peaks within your angle data set getting more variable. And anytime you have to sort of find peaks and measure the width of all of these peaks, it's going to be a difficult method to reliably do. And so, you can't simply calculate the standard deviation of the angle. You have to look at how many peaks you have, how wide are all of these peaks, and it gets very messy. Also, these systems are really synthetic, and so you very rarely have a system that's so nicely organized. Even if you're looking at something like the honeycomb structure of a beehive, and sort of what happens when you give the beehive, cocaine. Does the honeycomb structure get really disorganized, or does it stay the same? You don't have a perfect grid. You sort of have a quasi-periodic system, but it's not perfect. There will be mistakes, and presumably after you give the bees drugs or something else, then it will be even further away from this normal state. So now what we can do is we can look at a random system. So this is a system where we basically just have points randomly distributed throughout. It resembles real data much better, and it gets rid of all of these kind of symmetry problems that we have, where you can have a very small deviation that causes huge fluctuations. And so now what we can do for this is we can find the nearest neighbors as well. We have our system at 1, 0.6, and 1.5. And how would you expect the nearest neighbors to change when you apply this compression factor? So we knew it was a linear scalar when our system was perfectly ordered. What would we expect when it's sort of random? Yeah. The formula was just x prime y prime is alpha times x y.
Before it was going up just with alpha.
Right.
And now, in this case,
Yeah, exactly. So we wouldn't expect it to change because you're still applying the same kind of stretch to every system. You would expect the nearest neighbor distance to kind of scale with that stretch.
So what is, I'm sorry, I probably lost the line of thought. What's different from this system than previous systems?
This is random points.
Random,
The transform we apply is exactly the same, but instead of having a grid, we have random points at the beginning. Yeah. So that's what we switch here.
Random points which also can have, they don't have to have discrete positions. They can have points, real values. They don't have to have a discrete value.
Right.
So that's the big difference.
Well, the other points could have had irrational values as well, but it wouldn't make much of a difference for the results. The big change is that the points aren't in a grid anymore. They're sort of randomly spread out. And so what we see is that for the nearest neighbor orientation, we have sort of our nearest neighbor vectors. So if we show all the nearest neighbor vectors that we have before, the orientations are more or less the same. That's not changed, which we wouldn't really expect to change because we're scaling it uniaxial. We're scaling it the same in every direction, isotropically. And then when we look at the distributions that we have now, we have sort of a linear scaling going on. So this is what the distribution looked like before. This is with 0.6, and this is with 1.5. So it scales exactly with this factor that we scaled it by. And the angle with the orientation also scales with the exact same factor. So now we can do sort of this shearing to the same system. So we can take this random set of points and apply this shear transform. And so this is where we start to see why these techniques can be helpful, because you wouldn't have probably guessed that this was a sheared version of this. This just looks like random points before and afterwards. And so knowing exactly what transform we applied can help us understand what's happening to the system. With the linear grid of points, you could just look at the grid and say, this looks sheared. You didn't need any analysis to tell you that it was sheared. But with this, you can't tell that this is sort of a sheared random system. This is then very strongly sheared, so strongly that you can start to see that looks sort of like it's been sheared, but with this one it's not far enough that you can tell that easily. Cool. And so then you can see sort of the nearest neighbor vectors all shown on the same plot between 0, 1, and 3. And that's what the distributions look like. And so we see that the distributions change a little bit. And then when we look at the statistics, we see that the distances at 0 are sort of this curve. And as we start to shear it more and more, there's sort of a peak here that forms and then moves further away. It's not completely clear, but at least it's some small change that we see. And then we see in the orientations that there's a shift. So this is then plotted sort of on a polar coordinate, so we can see the distribution of orientations easier, and we can see that there's a bit of a shift here when we have these changes. It'd be difficult to quantify, but we can see that there are some differences. Now to do sort of this stretching transform, and so if you have this 0.5, this tries to cluster things towards the edge, and this 3 tries to cluster things towards the middle. And so we can see here that we do get very large changes in the length and the orientation in some sense, but not there as much, between these distributions, so that we see differences that come out there. And if we look at the distance, we see that this peak moves. And so this 1 is sort of the normal system, and this 0.5 and 3, that mean goes further and further away from 1 as the stretch gets increased, or gets further away. Cool. In the angles here, we don't see much of a difference, that they have more or less the same shape. There's a slightly different sort of mean, but not enough to be very significant. Then finally, kind of the swirl system, that you have sort of 0, 4, and 18. And you see here that the angles shift a bit. The distance doesn't look very much different, but this nearest neighbor distance then has another sort of small peak here that we see at 18, but would be kind of difficult to quantify. And the orientation, we see different peaks here, but how you'd actually measure that would be rather challenging. And if you had a different random system initially, it would be difficult to say what made this sort of a good sign that it has been swirled or strongly swirled before. You know, maybe having 2 peaks instead of 1 peak is a good indication, but it's pretty tricky. So basically the point of all of these slides was that the nearest neighbor tool is useful. We can see kind of how it can analyze these sort of systems, but it's limited in sort of these 2 test transformations that we applied. So it shows the compression very well for random and structured or very well patterned systems, but for more complicated transforms like the stretching or like this swirling, it doesn't work as well. And so this is where we come up with sort of these more complicated metrics. And so one of them is called Voronoi tessellation. And so this is where you sort of have a set of points. And so here you see a grid of points. And what you do is you define kind of the region around a point by all of the area in 2D or volume in 3D, which is closer to that point than any other points that you have. And so it's similar very much to this distance map. And typically you can actually compute them together. You can compute these regions and the distance at the same time. And what you get is that if you have a grid of points, then you have a bunch of squares that evenly divide up your space.
Sort of be like the social aspect of personal space, like how much space you have between an individual and anything else that's
right.
Okay.
So if you were trying to quantify personal space from like webcam images of people, you could identify all the people, and then you could perform a Voronoi tessellation to measure this area around each person. And you could see that in South America, it was half of what it is in Sweden or something like that. But it's sort of a tool that gives you a very nice way of quantifying that. You know, you could use nearest neighbor distance. So what's the distance you get to the closest person? And that gives you one metric for it. But it doesn't always describe it very well. And so what's really nice with something like Voronoi tessellation is that, you know, if you did nearest neighbor distance, you would see, okay, here's all the people, and this is the distance they get. And you'd expect to see a large change between, let's say, South America and Sweden. But if you wanted to assess, are there people, you know, is this uniformly distributed? Or do they stay further away from people when they can see them sort of straight ahead, and people on their sides don't bother them as much? That they wouldn't stand like face to face with a person, but they would stand shoulder to shoulder. That wouldn't really bother them.
So in this case, in that situation, how would a Voronoi tessellation look? Would you have a shape that was rectangular rather than, well, let's say,
Right, it'd be rectangular. Square. And so what this gives you is, rather than just a single vector, it gives you a whole area that describes sort of what, the personal space is of each one of these points. That's actually a good metaphor for that. And so for kind of a random structure, we can see that we get a bunch of different random shapes out of it. But what's nice is these shapes do kind of correspond with what we see in the system as things that are being really closely packed together and things that are packed much further apart. So these ones have lots of personal space, and these ones then have very little. And so you can then look at this region, and, you know, a simple metric you could take out would be area, and that would tell you how well or how closely spaced together your objects are. So we can then calculate density in sort of a new way with this approach. So before, the way we calculated density is we had the box size. So you divide a box as sort of from -4 to 4, -4 to 4 in y, and then you count the number of points in it. And then you divide the number of points you have by this area of this box. So here, you know, you have the density of whatever it might be. And what we can do now is we can calculate the density for each single point in the system. And so we do this by looking at the territory or personal space of each object and inverting it. And so the density at that point is equal to 1 over that territory. The only catch here is that when you're trying to calculate the density in the whole image, you can't simply take the average of the point densities. You have to add all of the territories together and then take the inverse of that to get the same as the density in the image. And so for those of you who come from physics or statistics, it's quite common that when you have this air propagation, that if you invert something, sort of the mean of 1 over x is not the same as the mean of x, 1 over the mean of x. Because if you have a really small point, if you have one point that has 0 territory, for example, then you have an infinite density at that point, but the average density in your system won't be infinite. The average density will be something finite. But anyways, this is just more when you're doing statistics on your analysis later, that you sort of are aware that when you calculate this individual density, that you can't simply add them together. And so if we go back to this original image we had before, all of these have exactly the same density, but now we can color the points by their local density, or their inverse of this territory. And so now we see kind of towards this core, you have objects that are very densely packed, and that's why they have sort of they have this purple value, which is then very high. And as you get closer to the edges, you have more of this white or yellow and red values. And that you see here, you have most of these values have kind of this light blue, and then at the edges, some of the values are a little bit higher. And so what this helps us do is look at this image and really say the density at each point or the density at this part of the image is this, rather than having to say the density in this fixed predefined box is that. And so what's nice is that you can now plot this distribution and you see that the density on the x-axis and what the average density in the image is. And so the average density is always the same, but this distribution in local densities can be very different. And here, for example, we see that the average local density is quite different than the average density in the system. So Delaunay triangulation is sort of the next tool we have, and it's really the same as this Voronoi tessellation. It's just sort of another or a dual way to look at this. And so this makes kind of the neighbors that we have in our system very explicit. And so basically what the Delaunay triangulation is these triangles that connect all of the objects in your system without ever crossing. And so if two objects' territories were touching, so if we go back here, if two objects share an edge, then they also share a line in this Delaunay triangulation. And so there's different approaches for calculating both of these, but once you have one, it's a very easy transform to get to the other one. We see here that because we're using this grid, we have kind of this problem that we've seen before, where it's difficult to define, or it's arbitrary if you define, are these 2 points connected, or are these 2 points connected? Because there's either a very, very small edge connecting this one and this one, or a very, very small edge connecting this one and this one. And once these two are connected, these two can't be connected anymore. And so with Voronoi tessellation, we don't see the problem as much, but with Delaunay triangulation, we see that this angle is sort of arbitrary. So we have, again, some of these problems that we've seen before, but it's not as serious as it is with nearest neighbor. And so now we can get sort of a connections at each point as this number of edges coming in or out of each point in this Delaunay triangulation. And so we can see that sort of in this random system that we have, in this system above, all of the points either have, they have kind of a fixed number of different neighbors. This one has 2, this one has 5, but more or less it's, 4 or 5 inside the middle. And here you can have points that are connected to many different objects, and you can have points sort of at the edges that are only connected to 2, and that diversity will be then much higher. So now we can do the same sort of analyses that we've done before with these random systems, and we can apply something like compression to them. So we have our system before, and then we so this is the system under compression. So this is the system under compression, and this is the system under tension. So this is when you stretch it out, and this is when you shrink it down. This is the system with low shear. So with low shear, nothing changes. You see so more or less the same. With high shear, you then get sort of this banding structure that shows up inside of your Voronoi spaces. So you can see that shear is fairly sensitive to, or the Voronoi tessellation areas and volumes are very sensitive to the amount of shearing that takes place. With stretching, it's sort of the same, because these give you kind of the density at each point when you apply this stretching so that they're not randomly spaced anymore, so that they sort of bunch towards the edges. You see that very clearly, that you have some much larger areas in the middle and very smaller areas towards the edges. Similarly, when you sort of compress them towards the middle, you see again that you get the very, very small areas here and the very larger areas towards the edge, or the larger areas towards the edges. Swirl, you get the same sort of thing, where after a high swirl, you start to see sort of structures and things getting closer together. that you hadn't seen before. We can also then look at the neighborhoods the same way. So if we have stretches or compression, the neighbors don't change at all. They stay exactly the same because they're just looking at the single points and what's connected. With stretching, the ones that are closer to the center sort of get more connected. The ones that are closer to the edges get less connected. With shearing, sort of the way these connections are oriented change quite a bit. And with swirling, we don't really see anything change in these neighborhoods. That they stay kind of random as before and after. So now we can look at some of these metrics and how they change in different systems. And so here we show the factors as different colors, and then we can see how the neighborhood count changes as you change these factors. And so here we see that for compression, the neighborhood doesn't change at all. It stays completely the same no matter what factor you apply. For stretching, you see that this neighborhood sort of shifts back and forth a little bit. And so that's where you're sort of non-linearly stretching, moving things closer to the edge or closer to the center. For shearing, you see that you start to get kind of more peaks as you apply a stronger shearing to the system. And swirling, you see some differences, but it's pretty hard to tell. For volume, we can do the same sort of analysis. So this is looking at this personal space. And as we shift this compression factor or tension factor, we see that that changes linearly with that. With stretching, it's sort of the same as we saw before, that they get closer together or further apart, and these volumes change correspondingly. Shearing, we don't see too much of a difference. Swirling, we see a couple more of these really high volume areas appear, but other than that, the distribution doesn't change too much. Cool. And so what we can do with all of this information is that we can kind of identify how these curves change as we change the parameters that we have in our system. And so if we change the stretching factor or the compression factor, this compression stays the same. The mean stays the same, and the variability stays the same. With stretching, we see that the variability at sort of a 1 or a standard system is in the middle. And as we take it away from this 1, the variability goes up. And the mean is then sort of linear with this parameter. We then can look at shearing, and we see that the variability sort of goes down strongly as this shearing becomes stronger and stronger, and that the mean doesn't change very much. And so basically these curves give us a way of sort of identifying what behaviors we see and bringing them back to this compression, stretching, shearing, swirling. And so the idea isn't, so the swirling we see doesn't really have too many trends that we can easily extract. But if you have an idea of what kind of transforms can take place in your system, then you can use synthetic systems to generate what would happen in these cases, under these circumstances, and then match up your results to the synthetic system which explains it best. And so, for example, this stretching that we have sort of groups things towards the edges or towards the center. But if you expected, you were looking at the bone samples from before, and you expected the cells to get closer to bone, then you could simulate that before, and you could show how that parameter changes, and then you can map your results back to that parameter changing to understand what happened in your system. And so if you have the opportunity to model it, you can simply replace these pieces with the pieces that make sense for your system, and then see what happens as you change those parameters, and then by measuring something like neighborhood count or area or the anisotropy of this region or whatever it might be, you can analyze this much better. Yeah. And so basically what we have is we have sort of these metrics that we've created and systems that we've applied them to. And so if you have a random system and you apply it, you can then see what meaningful metrics you can extract from it by looking at these values. And so you can take the mean values and see how the means change. You can also take this coefficient of variation. And so that was this looking at the variability, which you take the value and divide by the mean to see how much that changes. And if the variability goes up, as you have in a system like stretching, then you can identify that if the variability is increasing, then there's some sort of nonlinear distribution change going on. Right. And so this is kind of how we understand these ideas, is that we try to understand the rules that took place to cause the change that we observed. And so you sort of have these cells distributed in bone. Their position appears to be random, and you want to be able to define how did these positions change. Particularly as you get more cells or less cells, how did these come in or out of the system? And by using these tools, you can quantify that the cells, there are more cells than there were before, but there's also more total area, and so the density stays exactly the same. Or the new cells come where the density was low before, and so the density is more even than it was. And so these are the kind of sort of assertions you can make after you've done these analyses to understand what the differences you see in samples like this are. Because knowing that there's more cells isn't always helpful. You want to know where they came in to understand what factors could have been important in causing them to come in. Yeah, so here we have more graphics that show how all of this looks for different systems and all of the parameters that we have. And this is just for kind of reference in case you're interested, but it's not that important. And then you can see sort of, you can do a sensitivity analysis on all of these different metrics to see for many, many different random systems, how did these values change? And so we see for here that even with lots of different random systems, the trend in the data is quite clear. Or with this one, the trend in the data is really, really clear. The randomness doesn't change too much about the results at all. But for something like this result, the randomness kills basically any trend that you would see. That the noise or the variability from sample to sample when you use random samples is much higher than the values you can extract. So we can, this is then looking at stretching, shearing, swirling. And so we see is kind of, we'd expect with swirling, most of these values don't really hold up when you look at a lot of different random systems. But this territory change as you swirl it more seems to be a trend that you see. And so if you see a strong shift in this, it could be a swirling that was happening to your system. Now to kind of get into the last metrics that we wanted to cover, this idea of a self-avoiding object or self-avoiding distributions. And so when you look at how cells, for example, are grouped, you can quantify how well they're clustered together using something called the self-avoiding factor or self-avoiding coefficient. And basically, this factor is very commonly used in biology and material science. And what you do is you compare the observed nearest neighbor distance with what it would be expected to be in a completely sort of random point distribution. So if you know about Poisson point processes, you can model this very easily. But basically what you have is that the random distance or the mean expected value between points should be the cube root of the total volume over 2 pi times the number of objects. And what you can now do is you can compare the nearest neighbor distance to this value to get how self-avoiding the objects are. And so if this value, if the nearest neighbor distance is higher than this value, then the objects are further apart than you would have expected by sort of random distribution. And if the value is smaller, then the objects are closer together. And so it can tell you a lot about a system and sort of how well it's clustering or not clustering by comparing it to a completely random system. Okay, and I don't have graphics here, but if we go back to the density plot we showed before, I can try this now. that we can see. Well, with this one, it's not perfect. If we had a grid of points, that's about as high as you can get for self-avoiding systems. And so each point is sort of as far as possible from all the other points in the system. And something like this would then be very strongly clustered. And so the samples are much closer together than you would expected if you just sort of randomly distributed. These as well. They sort of have a very low self-avoiding coefficient. This one would have sort of a self-avoiding coefficient of probably around 1 because they were randomly assigned there. And if you had a perfect grid of points, it would be then much higher than 1. For calculating sort of this information, we've shown how we did sort of this 2D Voronoi tessellation and this 2D Delaney triangulation. And so now when we move this to 3D, it sort of becomes much more important to try to visualize these results. And so when we had this Voronoi tessellation, we had sort of these points and this area that was filling up around them. And when you do the Voronoi tessellation in 3D, you now have this volume. So rather than having a personal area, you have a personal volume around each one of these points. And what the distribution tensor allows us to do is to sort of characterize what this volume looks like in the same way that we did for the shape. And so it's kind of the analog of the shape tensor in the distribution space. We calculate it differently because for this we want to be able to use it in other approaches, and that's where one of these papers is being referenced, where it's used to calculate the stress and strain on given systems. And so what we use instead of the Voronoi volume, we use the Delaney triangulation, and we look at all of the lines connecting, sort of the vertices, connecting objects to the neighbors around it. And so then you can calculate the covariance matrix for all of these different vectors and come up with this distribution tensor, which describes how the objects are sort of spaced. We can then do the same decomposition we did before with the shape tensor, where you break it down into eigenvalues and eigenvectors and eigenvalues, sort of this principal component analysis that then tell you about your objects. And so the results we get from this are that if you look at sort of a bunch of randomly distributed points, like we have in the system, your distribution tensor is sort of a sphere. So you get a circle, a sphere out, where the anisotropy of this is very, very low because they're randomly distributed in every direction, and you wouldn't expect a preferential direction for these links to be shown. If we have objects that are distributed in sort of strings, so where they're close in one direction and far away in the other two directions, so this is kind of the average spacing that we have, you then extract the distribution tensor, and it gives you an oblate structure, so a very plate-like structure. And so you can look at the shape of this and say, based on this, it looks like the objects are kind of distributed in strings. Similarly, if you compress it in two directions, and they're really far in other directions, so if your object's made up of sheets, then you get a very prolate structure out. And so if you see that your distribution tensor is sort of a very rod-like or very elongated in one direction and small in the other two directions, then that tells you this is what your distribution looks like. And so with these structures, because they're sort of synthetic data sets, it's very easy to see. But if you want to be able to describe how these points are distributed, and are they distributed in a more plate or string-like or a more sheet-like structure, then you can use this distribution tensor to quantify that, and you can use the anisotropy and the oblateness factor to quantify exactly how much they look like strings or how much they look like sheets. And so it gives us just a lot more information on this. And usually where this is helpful is where you can kind of see some of these structures being present, and you need a tool to quantify how they actually look so that you can compare samples. And so if you have, 20 different samples of healthy patients and 20 different samples of sick patients, and you'd expect the healthy patients to be distributed in sort of the sheet-like manner, and it goes from being a very prolate structure to being a very isotropic structure, then you can show that with this factor. And so that's kind of the result that you get out of it. So yeah, you see the oblateness is calculated the same way you calculate oblateness for the shape tensor, and it tells you sort of if it's more strand-like or more sheet-like. And so it helps you extract that kind of meaning from your data. Orientation, so this is kind of the first problem we encountered, is that you can't really use the means and the standard deviations for angles very well, because no matter how you define it, you always end up with this discontinuity between 0 and 180, or 0 and 360, or negative 180 and 180, because you have to define sort of a certain point that's in the middle. And so we have sort of 3 different systems here. And if you look at them, you'd say this one looks pretty well aligned, this one looks not very well aligned, and this one looks really disaligned. But if you look at sort of the standard deviation values, it doesn't really indicate that very well, because the standard deviation of this one is 87 degrees. But when you look at the structure, it looks like everything's quite well lined up, and so it actually isn't indicating very well what you can see easily. And so, because orientation that we're looking at is derived from a shape tensor or distribution tensor or some other analysis, we don't have any label for heads and tails. And so the values that we're looking at are really the same in the positive and negative direction. And so we can't tell this is the top, this is the bottom, we simply know this is the angle. And so what we have here is we can show the vector of the primary orientations, and so that's what we can extract from these objects using the shape tensor or this elliptical model that we had before. And now we can show these distributions. And so by looking at these distributions, you can see visually, this one looks like it's fairly consistent along this one axis. This one's more distributed and this one's even more spread out. And so this is where we introduce the final kind of tensor that we'll have, and this is then the alignment tensor. And we see that this tool is very helpful for quantifying sort of difficult to quantify structures. And what we take here is we take all of the vectors that we had before and we put them together in a tensor. And so rather than taking all the individual voxel positions, as we did for the shape tensor, or the individual links of this Delanoy triangulation, as we did for the distribution tensor, we take the orientation of a bunch of different objects and calculate the covariance and then the principal component analysis to have the alignment tensor that describes this object. And so basically what we see is when we have these sort of slightly randomly oriented objects and we calculate the alignment tensor, we then get a really, really elongated structure that's oriented in the main axis direction. So basically it summarizes all of these different orientations together in one single object. As we start to make these objects more and more randomly oriented, we see that this alignment tensor gets more and more spherical. And so if it's perfectly spherical, it means the objects are oriented in every possible direction. There's no alignment. And the more oriented it is, or the more elongated it is, the more oriented the sample is. And so it basically gives us a degree of alignment that we want to have based on how anisotropic the structure is. So yeah, so we have the primary orientations. We can show it, again, showing the sort of anisotropy that we have as we go in 3D, where you have the orientations that sort of are distributed like this, like this, like this, like this. We see that this alignment tensor anisotropy goes from being almost 100% down to 30% for these ones that are fairly randomly distributed. And so it gives us a very solid metric for assessing how this changes. But yeah, so we can then apply it to the system, and we can then find the primary orientation direction and the degree of alignment that it has. And so here, this is very well aligned, and it's 99% aligned, and we see it's aligned along this axis. And we see that these other ones are aligned along certain axes, which may or may not really match well. And this one then has a 20%, and this one then has a 15% degree of alignment. Cool. We can then look at a bunch of different systems and show what the average alignment is, and we see is that it gets more random. This average alignment becomes less and less meaningful, but up until this point, it's very consistent, even though the values are getting more and more random. And we see that this sort of alignment angle is much more stable than the average value of the angle that we're looking at. And so we know that it's supposed to be 0, that it's supposed to be along this axis, and we see that this average angle just sort of jumps up and down, and this alignment angle stays fairly constant. And then we see that sort of as the angle variability sort of increases, this alignment drops down fairly consistently, where the standard deviation of the angle goes up a little bit, but it's not as clear of a trend. And if we were to look at different systems, it wouldn't hold up. And so this alignment is a much stronger factor for showing how well oriented a bunch of these points or a bunch of these objects are in a system. It also has the advantage that it works in 2D or 3D just as well. Cool. So briefly to kind of mention other approaches for looking at these sort of samples, you can also use kind of k-means to classify the point space, as we showed a little bit before, where you can kind of feed in more information about position and other parts of the sample to quantify it into different regions. 2-point correlation functions, I think we have part in the exercises which goes into a little bit more detail there. But basically you have these endpoint correlation functions that you can generate, and they're probability maps that say, basically, given that you have a point of type A, so whatever phase this point belongs to, at x, what's the probability of having a point of type B at a point x plus r? And so, for the example of bone, given that you have a piece of bone at x, what's the probability that you still have bone at x plus r? And so if you have large bone structures that are sort of close together, you'd expect them to be very well grouped, and that for this probability to be very high until you got really, really far away. If you had bone that was sort of spread out into small separate little dots that was randomly distributed, you'd expect this probability to drop off very quickly. And so what this map gives you is it gives you sort of a single curve that describes a lot about how your sample looks. And if your sample changes a lot, you'd expect this curve to change a lot as well. And I think, if I'm not mistaken, if we go... So a simple example of this, just to show it quickly. Is that if you're looking at something like a bunch of fibers in a system, so that you have 3 different phases here. You have kind of this core in the middle. You have the first shell around the fiber as this layer, and then you have the second shell around the fiber as that layer. So you sort of have this green, blue, and white. And you want to be able to describe this system well, that you could try to segment all of the different fibers and then measure what the neighborhoods of all of these fibers are, what's the territory or personal space for all of these fibers, and what sort of other objects come inside it, but you get very messy very quickly. And so if you're trying to measure how thick is this blue layer around the object, this is then a place where the 2-point correlation function can be very helpful for giving you that result very easily. And can anyone think of how you would formulate that? So we had basically, given a point of type A at x, what's the probability of B at x plus r? And how would you apply that to figure out what's the average thickness of this low density silicon carbon layer around this carbon core?
Well, you might see, for example, given you have a low density layer at any one point, what is the probability that its neighbor at a certain distance is also that? If the probability drops off very quickly, it means that that's a very thin layer.
Yeah.
If it's larger, not that.
Yeah. So that would be one way to do it. That would tell you a lot about the low density silicon layer.
And you're good at something similar to the others, or if you're in the center, the probability you have something that's not core nearby. If that probability is high, then that means that that core is very thin.
Yeah. So what we see, so the problem with what you mentioned is that when you look at just the blue material and say what's the probability,
Which way you go, you have white or green.
right? It could have white or green. And if you're looking, there's blue material out here as well. And this could be very thin. And that would then be affecting your average thickness assessment. If you had no blue material out here, that would work perfectly fine. So what
It
you,
would be blue probability, given blue, what's the probability at a certain distance you have green core? And that,
it's easier to do the other way.
the core, then your core you're trying to find the white.
Yeah.
Okay.
Right. So that you say, given that you're inside the core, what's the probability that at x plus r, you have white? And so what you can do for this is you can then generate these curves, and that you can see, given that you're in core, what's the probability that you have this low density material? And then you can see sort of this r goes out, that you have this flat part of the curve, and then it starts to drop off. And this is sort of the minimum inner layer thickness, and this is then the maximum inner layer thickness. So you can see directly from that curve the average statistics for the entire sample. You can then also see, if this were a question of light conductivity or conductivity, are there air gaps between this core and that first layer? You can then change this probability function to say, given that you're inside the core now, what's the probability that you have air? So this other phase, this black phase that we show here. And that then shows up as this green curve. And so you see up to 10% detachment here. So you do have lots of regions here where there is air between your core and your first layer. And so those are the kind of analyses you can get out very easily with these kind of functions. So it allows you to describe your sample with simple curves and average over all of these different cores that you have in this image very easily. Because to try to do this by looking at each core and then figuring out how the sample around that core looks and going on and on and on is very tedious. And if you have one core that doesn't fit or a wrong mistake, then you can get a completely wrong answer. And by generating these functions, you can then see very quickly in this function that, of course, once you get out here, the probability gets much higher that you have air. But typically you have the first layer and then the second layer, and you can measure the thicknesses or the variation in the thicknesses of these different layers and then continue. You can also see for structures like this, where you sort of have this randomly structured clay. And what you're interested in finding in this is which way was it compressed? Because this was sort of a sample taken out of deep in the earth somewhere. And as sort of gravity compresses the sample, it forms layers. So if you look at the system, your eyes can kind of see that there's this sort of structure that forms, but it's not very easy to see exactly where that is present or how you would analyze it. And so what you can do is you can make this radial distribution function where you say, given that you're in a clay, what's the probability that the point next to it, or given that you're in calcite, what's the probability that the point next to it is clay? And so you can then generate this distance from, and then you see, okay, this drops off like this. The further away you get, the less likely it is that you're still inside of calcite. And then you can look at these two curves and see that there's actually not isotropy, and so it's not the same at every angle, radial angle, that there's actually a point here where the probabilities sort of match up. And that corresponds to the fact that there's layers present in the structure, and that angle gives you the orientation of these layers. And so by looking at these maps and looking at sort of variations or fluctuations inside of them, you can start to understand these more complicated structures that would be really difficult to meaningfully analyze using a standard segmentation. Because if you can segment all of the calcite and all of the clay and all of the dense materials, it won't tell you anything about how they're positioned compared to one another or how you can extract meaningful values that way. Cool. So you won't actually have to do very much on this stuff. It was more to just cover it so that you're aware of these techniques because they can be useful in certain situations. Cool. So are there any questions over that last part of the material? Hopefully the assignments that you work on will make it a little bit more concrete, because when you actually practically apply these tools, it then becomes much easier to see to kind of get a feeling for what's going on.